Good morning all. Today we are going to see the production of three-phase AC supply. As we know that generators are the responsible to produce the AC supply, isn't it? The power system has the generating, whatever all the generating stations, whatever the generators we have, they are the responsible to produce the three-phase AC supply. And what is the principle of the generators here is the generators are work on the principle of Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Electromagnetic induction. So what is this Faraday's law and how your machine is working and how this machine is rotating? So those concepts will in detail we are going to deal in the when we are going to study the DC machines as well as AC machines. There we are going to see the details. But as of now, we will take that what is the Faraday's law for the generators concept here. So whenever the rotating conductor placed in a magnetic field it cuts the magnetic field, it cuts the magnetic flux, and EMF is induced in it. So this is the statement of Faraday's law of electromagnetic induction in case of your generator. So to understand this one, you can take, let us consider we have a magnet of north and south, have a simple magnet. I'm taking here north and south. Obviously that magnetic fluxes are going from the north to your south side. So these are the magnetic flux directions we assume. So these are the magnetic flux directions. So in this magnetic field, so this is what the magnetic field here. So in this magnetic field, the magnetic field, if you place a conductor, so this is my conductor. If you place a conductor and it is rotating, So whenever in a magnetic field, a rotating conductor, if you place in a magnetic field, it will cut this magnetic flux. If it cuts the magnetic flux, therefore this conductor, if it is a closed circuit conductor, then it is going to produce the current in it. Therefore it will going to induce the EMF. So that EMF is nothing but the generated EMF, and this generated EMF is a sinusoidal wave. So this is what we have talking whenever you are talking about the AC system, then that rotating whatever the EMF is generated by these generators are the sinusoidal wave. How these sinusoidal waves are going to be generating in any kind of generating machine. So that concept we are going to see now. As we know that if you have that machines, that is the generators, if you take any machine, generators, rotor, motors, whatever it is, but in case of generators we have the two main parts. One is called the rotor, and you have the stator part also. Stator and rotor parts will be there, and you can say on the stator part maybe you have your magnetic field type construction in the stator part. On the rotor part, so you are going to place magnetic field, you try to place the conductors. You can try to place the conductor somewhere here, some conductor. So this is what you can say the conductor. And how that conductors, and these are the nothing but your magnetic flux is going like this. This is the magnetic flux or magnetic field here we have. And whenever this rotor it's rotating, suppose assume in this direction, my rotor is rotating in this direction, therefore my conductors also rotates. This is a conductor, somewhere here you can say these are the conductor, different positions you can assume. So if this rotor is rotating, so whatever the conductor which is placed on the rotor will also going to rotate. Therefore this rotation of these conductors I can take is the velocity is v. The rotation of the conductor velocity is, I can take, it is the v. Then the EMF induced in the conductor, the EMF induced in this conductor can be written in the mathematically is nothing but B L V into sine theta. So that is what the EMF induced in your conductor in case of generators. So what is this here? Base, you know, obviously it is a magnetic flux, you can say a magnetic field, and L is the active length of the conductor, and V is that velocity of the conductor, how much velocity it is rotating, velocity of the conductor. Whereas the theta is nothing but, the theta is the angle between the magnetic flux and the velocity of the conductor. Theta is a angle between your magnetic flux and magnetic field and a velocity of the conductor. Now with respect to this equation, I just want to know whenever my conductor rotating at each and every point, what could be the my EMF induced by that respected conductor. So that is what I just want to clarify here. So for this, what I am trying to do is that again I will take that how my magnetic field I'm taking. This is my magnetic field direction I'm taking. So this is what the magnetic field direction. So magnetic field direction I'm taking, and this is my, we have that rotor I have, and the rotor we have that conductor. Suppose a different position I am placing my conductor here, and here. So these are the different positions I am showing my conductor here, and for the different position what could be the direction of the velocity of my conductors. So it is tangential with respect to this rotor. So this is what the direction. If it is a conductor, then this is the direction of my velocity direction of my conductor, and this could be that velocity or move direction of my conductor, and this is also velocity of my direction of conductor, and this is the direction of my conductor. I can show something like this, isn't it? Therefore if you see here, this is the velocity v, and this is the flux. So what is my actually the angle sine theta? So sine theta is the angle between B and V. I just want to confirm at each and every point what could be the angle between the V and B. If you see here, the angle between that here, so angle between our B and V at this point, the angle between the V and B is 90 degrees. Here also angle between the your V and B is 90 degrees. And here the angle between this one, because my flux direction in this direction, my velocity direction also there, so it is 0 degrees. And come to this one, my flux direction is going this one direction, my velocity direction this direction, but my flux direction, magnetic flux direction this direction, it is 180 degrees phase difference you can say. But when come to here, so this could be that flux this B direction, and this is my velocity direction, so obviously it is 90 degrees. When come to here, so this is my direction of B, but this is my direction of V, so here also you have the 90 degrees. So this is what the how that different conductor position, what could be the possibility of the angle between your V and B. So that is what I am just try to want to explain you. So you got that idea how it could be that reasons. Okay, let us take now. Let us take, I have again the magnetic field N and S we have, and this is my conductor. I have my conductor, and I have showing my conductors in different positions now, again showing in different positions. And what I'm assuming here is, so this is the first position, this is my second position, and this is my third position, third instant, and this is my fourth instant I'm assuming. And obviously whenever that current in a conductor, when it is in north pole, then this is going inside the conductor. If it is in the south pole, your conductor coming out from the conductor. So that is what the direction you can show with according to that Fleming right hand thumb rule. So you can write that one also, and come to this one. So this is what the directions now. So I just want to prove that my induced EMF is, or I just want to see whether my induced EMF is sinusoidal signal or not. That is what I just want to see, that one. So I'm going with the first position, and I will see what is my induced EMF in this moment. I'm going with the first point, and I will see what is the direction, this one. So I will draw, this is the line, this is the first position of conductor, second position of the conductor, third position of the conductor, and fourth position of the conductor, again first position of the conductor, because it is continuously rotating 1 2 3 4 1 2 3 4. So this is what the rotation of my conductor on the rotor, as we know. And assuming that this is the EMF, assume it is the EMF versus this position, or you can say angular theta or mechanical theta, you can assume that one. When at the moment, at the point A, at the point 1, if you see what is the relation between your, what is the angle between, theta angle between your B and V here in the point 1, at the place of 1, what is the angle between B and V here? Because this is tangentially going, and this is what my flux is going. So this is the direction of the flux. So in the theta between B and E is 180 degrees, isn't it? 180 degrees. And what could be the induced EMF? Sine 180 degrees. What is the sine 180 degrees? Sine 180 degrees is 0. So according to this, what is the value of our EMF? E B L B sine 180 degrees. So this is going to be 0. So this is going to be 0. So I can start from this point. So I can show here, this is the at the point of position 1, my conductor, when reaches to the position 1, my conductor, the EMF induced in the conductor is 0. When come to that second point, whenever my conductor rotates to or reaches to the second point or second position, then the angle between the B and V is the 90 degrees. At the time, the angle between the B and E is 90 degrees. Therefore, if you apply the 90 degrees here, so therefore the maximum amount of EMF can be generated. So maximum you can show here. Again come to the third point here. During this rotation, my conductor now reaches to the third position. At this moment my EMF is again 0. And come to the fourth position here, again my EMF is maximum, isn't it? Because here also it is a 90 degrees angle between your B and V. It is maximum, but I take it is a maximum, but it is in negative direction, because in north pole side the current in the conductor is going towards the inside the conductor. When my conductor reaches to the south pole, my current direction outwards the conductor direction. So therefore the current direction is different in the north pole and south pole, but anyhow the maximum amount of EMF is generating. Therefore just why it is coming in the a negative direction, I just want to show you. Again come to the first point, again it is showing that as 0, isn't it? So this is how, as on it is completely rotating, my sinusoidal signal is going to be generating like this. So this is what the EMF it is. Whenever my conductor is rotating, this is going to be generating in a sinusoidal signal is generating in a machine. So you can say it is a EMF generated by EMF wave. It is generated by your signal, or you can say it is that EA is equal to EM into sine omega t. You can talk something like this, em into em sine omega t. Here you can say like that, because only we have taken the single conductor coil. We have taken the single conductor coil, that is, assume it is a coil. A coil we have taken, that is the single conductor coil. For that single conductor coil, one sinusoidal signal we are trying to producing that one. So this is, you can say it is a single phase, you can say it is a single phase AC system. Single phase AC system, you can say, have the single coil. If you place it in the rotor and do the generating machine operation, therefore it is going to produce the single phase AC system. So this is what it's going to show here. What is the point you need to understand here is, you take one note here. So whenever my conductor rotating in a magnetic field, whenever my conductors are rotating in this magnetic field, then EMF is maximum. EMF is maximum when the conductor comes under north or south pole. But the EMF is zero. EMF is zero when the conductor is in between. The conductor is in between the poles. So these are the 2 points we observed, isn't it? If you see here, when the conductor reaches to that north pole or south pole, their EMF is maximum, and whenever the conductor in between your poles, these are the 2 poles, in between these 2 poles, if it is here and here, then your EMF is 0. So that is what, so that's why you are getting this kind of signal here, sinusoidal signal. So that is the point you need to understand here. So this is the simple understanding purpose of how to generate the sinusoidal signal, how it is exactly generating our generating station, the sinusoidal signal. And this is the operation for in case of your single phase machine. If it is a single phase generator, this is the operation. If it is a two phase machine it is. If it is a two-phase system, then what could be the operation, and that is what I just want to show. So I will take that magnetic field. So this is my magnetic field I am taking here. I have that magnetic field. Obviously, whenever the magnetic field is there, and your magnetic flux lines will start going from the north to south pole. So this is the direction of magnetic flux or flux lines you can show. And in between here we are placing a conductor. You can place a rotor. This is my rotor we have here. On the rotor we are placing the two winding coils. I'm going to place here. So I am going to place the two winding coil A dash and B dash. So this is A and this is A dash. This is one coil, and this is B. This is B dash. This is another coil, B and B dash. This is A and A dash, and this is B and B dash. That is what I'm placing the two winding coils here now. I just want to generate the two phase system. I'm putting the two winding coils. It is simple. You can show. This is called it is a single conductor having it is A and A dash. That is what I'm showing here. This is you can say it is a conductor. It is a conductor or conductor coil. So this is what the placed here. So have that A dash and B dash, two conductors I am placed on the this rotor of this machine now. So as you know that for the conductor A, we already generated the EMF, isn't it? The first phase, the first single phase, that concept we know how to generate this one. So this is what the already EMF has been generated. This is for B. When come to that second coil here, if you see what is the difference, angle difference between these two coils now, can you say what is exactly the angle difference between these two coils here to here? How much the angle difference is there? Can you tell me from A to B? So angle, exactly the angle difference between your B and A and B coil is 90 degrees, isn't it? From this point to this point to this point, if you take here, this is the B dash and this is B. So this point to this point, the angle displacement between your B and E is nothing but 90 degrees. That is what. And if my conductors are rotating in this direction, if my conductors are rotating in anti-clockwise direction, then I can say my B lags A by 90 degrees. Can I say? Yes, because my conductors are rotating in this direction, but my A is ahead of the B by 90 degrees, or my A is leads by B for 90 degrees, or my B lags A by 90 degrees. This is what the 90 degrees lagging my B with respect to the conductor A. So therefore obviously, so at this point which is lagging, means I have to start my waveform from a 90 degrees lagging here. So pi by 2 is the my point, reference point I have to take. So at this moment, so this is the conductor of the B coil, but it is in between the north and south pole. Obviously the EMF generation is minimum here. Now suppose it is going in the rotating direction, then B is going to become here after some times, then it could be maximum coming here, maximum comes. Again my coming here, again it is coming at 0 point, again it is rotating my B point, again it will come to a maximum value here, somewhere here, maximum. So maximum point here, something like this. So this is called the another waveform which has been created by your conductor B. It is created by your conductor B, and due to your conductor B, this is the sinusoidal signal you are going to get. Now will you write the what is the EMF generated by a coil? The EMF generated with respect to the A coil, A conductor, is that EM sin omega t. But what is the EMF generated with respect to the B coil here? It is EM sin omega t minus pi by 2, or omega t minus 90 degrees. You can say like this. So this is how the this is phase 1. This is the phase 1, and this is the phase 2. That is what the two phases has been generating here. So that is what it is called two-phase system. In the two-phase system, the phase 1 and phase 2 are displaced by a 90 degrees each. They have a displacement of 90 degrees. That is, or you can say 180 degrees by n. N is nothing but a number of phases. If you write, that is nothing but displacement. If you put single phase, you put the 2 here, two phase, 180 by 2, it is 90 degrees displacement between the two phases. If it is then it is if it is 3 phase, then 180 by 3, it is 60 degrees, you can say. So this is how you can show the difference between this concept, or you can say over here. Now similarly, if you go for the 3-phase system, what could be the 3-phase system here? So if you talk about what is the 3-phase system, here. So obviously for the 3-phase system, again we have the diagram for this we have diagram, and this diagram we have first phase coil, that is A dash, and this is the B coil placed on the rotor, B and P dash. This is nothing but the C coil, or third phase coil. This is C and C dash. So this is what the placement of the coils A, B, C, 3 conductors has been placed like this. and whenever it is rotating continuously, this is in direction, it is rotating. With respect to this rotation, according to the position of the conductor at each point, what could be that, you can see here, you can see obviously that A phase will be this one, you can say, so 0, you can say it is pi by 2, it is pi, and it is 2 pi by 3 pi by 2, you can say it is 2 pi. So this is what the can show this one. Now what about the second phase? You already know what is the second phase, can be start from a you can say here, but here it is, because what is the difference between the, what is the phase difference between your A and B? If you see here, so from this point to the here, if you see, so this is what the phase difference between your B and A. It means my B here, in case of this three phase system, my B lags A by 120 degrees. My B lags A by 120 degrees. Similarly, if you see here, my C lags A by 120 degrees. Sorry, 240 degrees. But my C lags B by 120 degrees. So these are the different lagging condition you can see with respect to this system now. Okay, now we'll see how to draw this waveform. So obviously my now A has been drawn and my B is lagging by 120 degrees. So my B is lagging by 120 degrees, means somewhere here it is a 120 degrees, isn't it? It is somewhere here 120 degrees. From here my B will going to start. My B is going to start and is going like this. So this is called my B. You can say this is my B, and this is A. And what about my C? C waveform is lags with respect to A. My C waveform lags with respect to A by 240 degrees. So 240 degrees, obviously I can show that 240 degrees somewhere here, isn't it? You can show somewhere a point, maybe here, you can show somewhere here. So this is what the third waveform is going to be showing here. So this is coming like this, and it goes somewhere like this. So this is what the third waveform is going to show here. This is the C phase. So now we have the three phases are available to you. So A phase, B phase and C phase, you can see here. And what is the EMF equation? How will you write that EMF equation for each one? So I can write for the EA, which is that EM sin omega t. What is the EB here now? EB is nothing but EM sin omega t minus 120 degrees. And EB is EM sin omega t minus 240 degrees. So this is the, you can write in sinusoidal trigonometrical form, or you can go into polar form, then EA into magnitude of 0 degrees. It is the polar form, EB with the magnitude of minus 120 degrees, and it is the magnitude of it minus 240 degrees. Like that also you can write here. So if you observe the three-phase system here, so some beauty of this three-phase system, you can assume some points here. Suppose if any two phases are intersecting, at this moment the one of the phase is going in a maximum value. It may be positive or negative, but it is going to a maximum value. So you can see that concept here also. There you can see, whenever the two phases are intersecting here, but my one of the phase is going to a maximum value. Maximum, it may be negative or positive. Similarly you can see, so this is the two points, this is the maximum value. So this is how, so as a result, the sum of the three phases is going to be equal to a 0. So in case of three-phase system, the sum of the phases, if they are a balanced system, then sum of the phases you can always be equal to a 0. So that is what the property of this system. So let me to summarize the what are the points you have observed from this diagram here. You have the two waveforms are intersects. If the two waveforms intersects is a negative, then one getting into maximum value, getting a maximum positive value. So that is what the first case you can see here. Two are intersecting in negative point, then one of the waveform is going to a maximum positive value. Similarly, you can say here, if it is my same point here, but if the two waveforms are intersecting at the positive value, then one of the waveform getting the maximum negative value, isn't it? Maximum negative value. So this is what that second point we observed here. The this waveform and this waveform intersecting at a positive points, then one of my waveform, it is going to be at the same instant, it is going at the maximum negative value. So that is the point you need to understand. And you can say it means that always sum is equal to 0. Always sum of the all the faces are equal to so 0. So this is the one of the property you can talk. If it is a balanced system, then you can say this kind of thing. If you want to show this EA, EB, EC, and EC in a vector form or phasor form, then how can you going to show them? Because in the three-phase system, the EA, EB and EC, three phases are displaced by 120 degrees. These three phases are displaced by a 120 degrees, isn't it? So this is what we have seen here. Displacing of these are 120 degrees with each other, the displacing with a 120 degrees each. So that is what just want to show here. So this is suppose A phase, it is a B phase, and this is the C phase. Between this 120 degrees, in between these two 120 degrees, in between B and C also 120 degrees is there, and assume my vectors are rotating in this direction. This is what the vector rotation I'm assuming in counterclockwise direction. So this is the case for balanced system. For balanced three-phase system, the three phases are displaced by a 120 degrees each. 120 degrees is. So this is how you can talk in a very brief manner what is in a three-phase system, how exactly it is generating in our generating station, and how it is going to be transmitting through the transmission line to the load. So that is what. Now what is the advantages of this three-phase system? Why actually want to go for the three-phase system rather than the single-phase system? So that is what I just want to discuss here. So advantages of three-phase system rather than the single-phase system. So you take the first point here is the output of the three-phase machine is nearly 1.5 times the rating of the single phase machine of the same size. So that is the first point I just want to talk. So what is meaning of this point here is, suppose have the machine of the same size, both have the same size, but it is meant for the single phase, it is meant for the three phase, suppose, but size is same. Size is same means the cost incurred to manufacture these two machines is same, cost is same. But what is the output? But output, suppose from this machine if you are getting a 100 megawatt, suppose you say 100 megawatt of power if you are getting, with the three-phase system with the same size machine you are going to get a 150 megawatt of power. So that is the economical advantage, or the more power can be generated with a more economical way. So that is one of the interesting point you need to understand here. The second one is the constant power can be delivered irrespective of the load. So constant power can be delivered irrespective of the load, condition, because if you have the three-phase system, there could be sometimes the load may be more on the A phase as compared to B and C. Therefore, there could be some load unbalance could be happened. Even though the three-phase system there is a load unbalance, but still the constant power can be delivered by this three-phase system as compared to your single-phase system. That is also one of the important advantage of this one. And another one is this three-phase system is more reliable. Why I am saying it is reliable means, suppose have a generating station, have the three-phase system is going. So this is my only single-phase system, assuming that three line is there. So here I'm having that connecting a load here. So have the load something. Here also having the load here. Suppose the fault occurs, some kind of breakdown occurs, then what happens? Completely it is going to not to supply any power to this load. If a fault occurs on this line, then it is not going to supply any power to this load. Suppose the fault occurs on any one of the line, then what happens? So it can be removed, but with remaining two phases, this load can be survived. So that is what the three-phase system is more reliable also. The third point is last point also you can say it is more economical, as we know that it is. So generating a three-phase power is more economical as compared to your single-phase generation. So these are the main advantages and what is the different type of the machine. So with this class I will stop for today's session, and I hope you have understood what is meant by three-phase system, how it is going to be generating, and how the sinusoidal signal of three-phase system is providing or could be generating from your generators. Thank you.